Okay, this video is about group 7, also called the halogens. So here's group 7. We have fluorine, chlorine, bromine, and iodine. Okay, those 4 elements. I'm going to ignore astatine there because that's a very, very small amount of it only in the Earth's crust. It's radioactive. And somebody's worked out 30 grams of it in the entire Earth's crust. And this one here, well, that's an artificially created element. It was only made about 2002 or something, so we won't talk about that. So we've got fluorine, chlorine, bromine, and iodine. Now, they've all got 7 electrons in their outer shell. So, for example, fluorine has got electronic structure 2, 7. Chlorine is going to be 2, 8, 7. So that means they all want to gain an electron in order to get noble gas electronic configuration. So if we look at how, so obviously they can get that that electron from elements such as metals, which give away electrons. So let's just see the reaction between sodium and chlorine then. So we're going to get sodium, which should have the electronic structure 281, and chlorine, it's always Cl2, so let's put a 2 there, and we're going to get 2 NaCl. Well, the electronic structure of chlorine there is 287. So 1 electron is transferred to chlorine from sodium. So here, this sodium chloride actually exists of a positive sodium ion with the electronic structure 28, and a negative chloride ion because it's gained an extra electron with electronic structure 288. So both elements have gained noble gas electronic configuration. Okay, now you may be surprised initially until you think about it to hear that when you go down the halogens group, they don't get more reactive, they become less reactive. So it's not the same pattern we get with group 1 with the reactive, with the alkali metals, where as you go down they become more reactive. And let's look at the reason for that then. Right, if we think about fluorine, right, it's I'll just draw fluorine here. Fluorine is a small atom. It's got electronic structure of 2, 7. So it has to attract the extra electron into shell 2. Chlorine is going to be bigger than that, and it's got the electronic structure 2, 8, 7. So when it attracts the extra electron, when it reacts, it's going to attract it into shell 3. Okay, it's going to be easier for fluorine to attract that electron in there because the positive nucleus in fluorine, drawn there in blue, is closer to where the electron is going to be attracted. Yeah, it's closer, so there's more of a pull from the nucleus to pull in the electron. Whereas with chlorine, it's further away, and also the pull of the nucleus is, use this word, is shielded. It's blocked to some extent by the intervening shells of electrons. And when you go to bromine, that you won't write down the full electronic structure of bromine because you don't need to know it. It's a bit more complicated, but bromine is going to attract the electron into shell 4, and iodine will be into shell 5. So that is why they get less reactive as you go down the group. Right, that's in contrast, as we say, to the alkali metals. So we think lithium is 2,1, sodium is 281. Those elements want to lose that outer electron. So it's easier for sodium to lose it because it's further away from the positive nucleus than it is in lithium. There's less attraction with the positive nucleus for that outer electron, so it's easier for sodium to lose it. So that makes sodium more reactive than lithium. Okay, let's have a look at the physical states of the halogens then. So I'll just get this table here, make it a bit bigger. Right, we can see they all exist as diatomic molecules. Okay, diatomic molecules, that means you've got 2 atoms joined together with a covalent bond, right? And you can see there's a clear trend in boiling point there. As you go down the group, the boiling points get higher. As they get bigger, the molecules get bigger, the boiling points get higher. And that's always happens in chemistry. You know, as molecules get bigger, intermolecular forces between them are stronger, generally speaking, and so the boiling points get higher. So fluorine is a gas at room temperature. Chlorine is a gas at room temperature. Bromine is as you can see, their boiling points are 59 degrees C, so room temperature 20. It's actually a liquid, but it's giving off a lot of vapor. It's bromine vapor. Iodine is a grey solid, and it actually sublimes at atmospheric pressure if you heat it up in a tube. It's 184 degrees, and it gives a nice purple vapor. So a little bit of a trend here that they're all coloured, all of these, all of the elements. They all have quite a distinctive smell. Well, fluorine wouldn't have a distinctive smell because no one ever smells it, because it's very rare to have fluorine. It's so reactive. There's very few labs in the world can actually deal with fluorine. It's just so reactive. But chlorine, we all know that chlorine smells a bit sort of like swimming pools. If you smell, they're all very poisonous. You don't really want to smell them. But if you ever smell a little bit of bromine, that has a very similar smell to chlorine. And iodine, if you take the lid off the solid iodine jar and smell it, it smells a bit kind of chlorine because it's giving off a little bit of iodine vapor there. They're all poisonous, so you shouldn't really deliberately smell them. So similar, we've got a trend in physical properties there. Right, now let's look at the reactivity of the halogens. They undergo displacement reactions. We've probably come across metal displacement reactions already, so it's a similar idea. Okay, so what we've got here is we've got a solution of potassium bromide, right, in this first diagram here, and we're going to add to it. That is called chlorine water. So it's actually chlorine dissolved in water, so Cl2AQ. Chlorine is pretty soluble in water. Now when you add the chlorine to that potassium bromide, and note that this is a colorless solution. A lot of people think, oh, because bromine is brown, potassium bromide is going to be brown. It's not. It's colorless. When the halogens are in their compounds with metals, they tend to be colorless. If you think of sodium chloride salt, it's white crystals, dissolve it in water, it's colorless. Yeah. Right, so you add the chlorine to that, and what happens is this will go reddy brown. And the reason why it goes reddy brown is because you produced bromine in aqueous solution. So if you write an equation for that, what's happening is KCl, so we've got there KCl, aqueous solution, sorry, KBr, beg your pardon, KBr in aqueous solution will react with chlorine in aqueous solution, and it will make bromine, the element bromine, diatomic bromine, and potassium chloride in aqueous solution. So you can see here that the less reactive halogen, bromine, has been pushed out of its compound by the more reactive one, chlorine. Okay, just like in a metal displacement reaction. Of course, if you remember the order of reactivity, so fluorine is the most reactive, then chlorine, then bromine, and finally iodine. Right, so here is a second experiment which you can do. Here we've got a potassium iodide solution. Again, that's completely colorless. And this time we're adding bromine water. So that's bromine dissolved in water, which is a reddy brown color. Now you add some bromine water, and what happens is you get this very nice dark brown solution. Now, iodine is confusing because when it's in solution, it's brown. When it's a solid, it's gray. When it's a vapor, it's purple. So you have to remember those three different colors. Okay, this is the brown solution you use in biology to test for starch. You add it to starch, it goes blue-black, so it's that browny colour. Now let's see what the reaction was there. So we started off with Ki in aqueous solution, and we add some bromine in aqueous solution, Br2 diatomic. That pushes out the so you get KBr in aqueous solution, and diatomic iodine is released. Now, just to balance that, we need to put a 2 there and 2 there. I think I forgot to balance the other one, didn't I? So I'll do that now. It's the same again there. You've got to balance that by putting a 2 there and a 2 there. All right. So 2 displacement reactions there. If we try to do it, for example, trying to see, we added, so we have potassium chloride aqueous solution, and we added bromine. Well, there would be no reaction there because bromine is not as reactive as chlorine, so it can't displace it from its compound. Okay, so you get a series of displacement reactions which demonstrate the relative reactivity of the halogens. And just to reiterate, they get less reactive as fluorine, chlorine, bromine, iodine as you go down the group.